Hello! In this video, we are going to prove the following theorem. Let A be an m by n matrix, and let K and L be real numbers. Then the matrix K times LA is equal to the matrix KL times A. Now, let's first remind ourselves our definition of scalar multiplication, where we do a scalar times a matrix. Let A be an m by n matrix, and let K be a real number. We define the m by n matrix Ka as follows. So for each pair of integers I and j, where I is between 1 and m, j is between 1 and n, the ij entry of matrix Ka is equal to K times the ij entry of matrix A. So all we're doing here is we're taking each of the entries of matrix A and multiplying them by K. That will give us matrix Ka. Now, notice each of these guys are the result of performing scalar multiplication on a matrix, namely matrix A. Right? First, we have our m by n matrix A. Then, multiplying A by L, we get the m by n matrix LA. But then taking the m by n matrix LA and multiplying it by K, we get the m by n matrix K times LA. What about on the right-hand side? Well, KL is a real number. So really, this is the result of performing scalar multiplication, multiplying the m by n matrix A by the real number KL. That will give us the m by n matrix KL times A. Right? So now, we want to show that these two m by n matrices are equal. Now, what does it mean for two matrices to be equal? It means that they have the same corresponding entries. More precisely, it means the following. Given that A and B are m by n matrices, then A is equal to B if and only if for every pair of integers I and j, where I is between 1 and m, j is between 1 and n, we have that the ij entry of matrix A is equal to the ij entry of matrix B. So really it just means that they have the same corresponding entries. Okay, so now let's get into proving this theorem. Now our whole goal is to show that these two m by n matrices are equal, which means we want to show for all I and j, the ij entry of this matrix is equal to the ij entry of this matrix. So to prove that, since we're trying to prove a statement about all I and j, let's give ourselves arbitrary I and j. From here, we want to show that the ij entry of this matrix is equal to the ij entry of this matrix. So let's write out the ij entry of this matrix. So then what can we do with this? Well, we can apply our definition of scalar multiplication. By definition, the ij entry of matrix K times LA is equal to K times the ij entry of matrix LA. So really, we can just pull the K out, and we get this. But then we can apply the definition of scalar multiplication again, right? By definition, the ij entry of matrix LA is equal to L times the ij entry of matrix A. So really, let me just group together, keep in parentheses what we have here. The ij entry of matrix LA is equal to L times the ij entry of matrix A. Just like that. So notice right here, we're just multiplying real numbers, right? We're just multiplying numbers. So we know that the associative law holds when we're dealing with multiplying numbers. So we can move the parentheses around K times L. So we get this. But then we can apply the definition of scalar multiplication again, because we see that KL times the IJ entry of matrix A is precisely the IJ entry of matrix KL times A. Right, we're just moving the KL inside the parentheses of A, so we get this. So, putting this all together, we have shown, given arbitrary I and j, the IJ entry of this matrix is equal to the IJ entry of this matrix. Since I and j were arbitrary, we can conclude for all I and j, the IJ entry of this matrix is equal to the IJ entry of this matrix. But that's precisely what it means for these two matrices to be equal. And so we're done. This completes the proof. And so yeah, that's pretty much it for this video.